All right, so we're going to hit up that zinc copper reaction that we did first when we drew our diagram at the very start of the chapter. So our half reactions, after balancing them, remember they look like this. Reduction was Cu2 plus plus 2 electrons, making Cu as a solid, and the oxidation part was Zn2 plus aqueous, Zn as a solid, making Zn2 plus aqueous plus 2 electrons. So we got to the point where we had our balanced half reactions. We added them up after canceling the electrons out. So we had Cu2 plus Zn as a solid, making Cu as a solid plus Zn2 plus aqueous. So that's usually part of the problem. A lot of problems you get are balance the equation and calculate E0 for the cell. So the balancing the equation part we did. This is our overall balanced electrochemical equation. Now we want to calculate E0 for the cell. E0 for the cell represents the ability for that cell to do work. If the oxidation and the reduction parts work right, and it's galvanic, you're going to end up with a cell that can do work. And the E0 for the cell measures that voltage. It's kind of like knowing what the voltage of your battery is. So E0 for this cell we calculate with our reduction potentials for each of the half reactions. So now we go back to our table in our book and we look up the cell reduction potentials for each half reaction. So when we find these in our table, we got to look for Cu2 plus doing a 2 electron reduction. So when you'll hear the terminology, look up the reduction potential for a 2 electron reduction of copper 2 plus. So we go here and we find copper 2 plus as our reactant. Cu2 plus 2 electrons, making Cu as a solid. That's exactly what we have as our half reaction. That occurs at plus 0.34 volts. Now we look up the analogous potential for the zinc. Zinc's being oxidized, but this is a reduction table. So we're looking up the 2 electron reduction of zinc in the table. So we find zinc 2 plus as our reactant. And find it absorbing 2 electrons to become zinc as a solid, happens at minus 0.76 volts. Notice I'm referring to this as the reduction potential for each one of these, even though there's an oxidation process going on. It's important that you don't change this to oxidation potential. It's possible to solve them this way, but I think it's more cumbersome. My way is better, and I think you'll agree after you give it a shot. So we looked up the reduction potentials for each one and left them as reduction, even though one of them is oxidation. Remember, like I mentioned before, if you flip an equation, you flip the sign on E0 for it. So instead of you manually flipping this sign because you know it's oxidation instead of reduction, we're going to plug it into a formula. And calculating E0 for the cell is really easy once you've looked up your numbers in the table. So it's E0 for the cathode minus E0 for the anode. And the reason why at least I write them that way, instead of the reduction minus the oxidation that we've got going on up here, labeled as reduction and oxidation, is because we don't want to confuse E0 of reduction and E0 of oxidation that we might be able to convert that one into. So it's E0 for the cathode half reaction minus E0 for the anode half reaction. Oxidation always occurs at the anode. Oxidation and anode both start with a vowel. Reduction and cathode both start with a consonant. Whatever mnemonic you need to keep them straight, but you got to keep them straight. The negative sign here does the sign flipping for us. So we don't do any sign flipping of the table values. We plug them in as they are in the table, including the signs. And the equation takes care of the hard work for us. So in this example, E0 for the cell will be E0 for the cathode half reaction plus 0.34 volts minus the E0 for the anode half reaction. It's the reduction potential of the anode reaction. So it's minus 0.76 volts. Signs are critical. The formula is easy, but the signs matter a lot. Okay? And when you plug this in, it's 0.34 minus 0.76 and flip the sign to make it minus. Okay? So type that through. Make sure that you get plus 1.10 volts. And electrochemists keep the sign with it even when it's positive. They write it as plus a lot of times to make sure that they know that they've gotten their sign, they've carried everything through, and the people that are looking at it know that they've done that check, that it is a positive potential. So the E cell for this reaction is plus 1.10 volts. When E0 is positive, E0 for the cell, or E0 for any of the half reactions. When E0 is positive, it is spontaneous. So this reaction, look back at the very first diagram you drew for that cell. When you hook up the wires and let electricity flow, it flows galvanically because E0 is positive for the cell. Looking at our individual half reactions, E0 for reduction for copper is positive because copper wants to be reduced. It's a jewelry metal. It likes to stay in the reduced form whenever it can. Zinc does not like to be reduced. Zinc likes to be in its ion form, its 2+ form, because the reduction potential going from Zn2+ to zinc 0 is negative. One other way to think about this is that copper will reduce when there aren't very many electrons around. A plus 0.34 volt potential means there aren't many electrons to scavenge. It will scavenge electrons when there aren't many around. Zinc, on the other hand, zinc likes to be reduced. Zinc likes to be oxidized. You have to force electrons onto zinc. You have to push them on with flooding it with electrons, pushing electrons onto it. Okay? It requires a minus 0.76 volt potential to be reduced. That means it likes to be oxidized because it likes to do the other thing, right? So anytime that E that you calculate is positive, it's spontaneous. Whether it's E0 for a cell overall, that means the cell is spontaneous, or a half reaction. This half reaction is spontaneous. This reduction is not. The way we've written it, it's spontaneous because we flipped the reaction. This is the oxidation reaction. And we flipped the sign when we plugged it into our calculator. That's where we get the 1.1 volts. Both of these processes are spontaneous. The table values are not because they're both reduction potential values. So that's the thing you have to keep straight. It's an oxidation half reaction, but we're looking up a reduction potential. I keep saying that because it's the easiest thing to screw up. When I was sitting where you are trying to learn this, I had a devil of a time with electrochem. It just didn't make sense to me until finally it was literally like turning on a light bulb and it clicked. Okay? But it's important to know that it's always cathode minus anode for a cell. You look up the cell potential tables, cell potentials in the table. You don't flip the signs up here. You let the minus sign in the equation do that for you. Okay?